Hi everyone, welcome back to our physics live webinars. We're going to have a session today run by our tutor Preshayla, and it's going to be on current and potential difference. If you joined us last week for Preshayla's session then you know a little bit about her. She's a student at Loughborough University and it's her 4th year tutoring. So I'm going to hand over to Preshayla, who will be able to lead the session. And just before I do that, she's going to be covering, for the first 5 minutes, recapping the circuit symbols, then understanding the meaning of current and potential difference, understanding the equations that govern them, and then understanding the difference between non-ohmic and ohmic conductors, running through some example questions, and then at the end there will be 15 minutes as always for questions. Just to say, if it's your first time joining us, welcome. These sessions run for an hour, and also to say that they're all recorded, so you'll be able to get a link so you can watch it back as well afterwards. And yeah, I'm going to hand over to Preshayla now.
Hi everyone. So yeah, as Frederica said, my name is Preshayla, and today we're going to be doing a little webinar on current and potential difference. So let's jump right in. The first thing I have for you is a circuit symbols quiz. So it's a quick little quiz. I'm going to give you 3 minutes to have a go and name as many of the circuit symbols as you can. You can write them down, you can just think about them in your head. But I'd like you to go through each one and think about what they represent. And as an extension, think about their function. So 3 minutes to do that. Okay, great. I'm going to stop you there. It looks like some of you are getting the correct answers, which is really great. So don't worry if you didn't get some of them. We're going to go through the answers now, but it is really important that you know what every single one of these means, because they could come up in an exam question and they might not tell you what they mean. So here are the answers. You can check if you got them right. The first one is a switch, open and closed. A cell, when you have more than one cell, you have a battery, so a cell there and a cell there. A diode, you can remember this because the arrow is facing one way, and diodes only let current flow in one way. We have a resistor, we have a variable resistor. Then we have a light emitting diode, a lamp, a fuse, a voltmeter, an ammeter, a thermistor, and an LDR. Now, don't worry if you don't know what the last two are. That's kind of what this lesson is going to be about today. Okay, so now that we know our circuit symbols, or refresh them, we're going to talk a little bit about current. So you might already know that electric current is the flow of electrical charge, which comes in the form of electrons. Now, the equation that governs current is charge flow, or Q. So charge flow is Q, capital Q, equals current, which is I, times time, which is T. Okay, so our equation is Q equals IT. Now, Q, the charge flow, is measured in coulombs, which is denoted by a capital C. I, you might know, is measured in amps, which is a capital A, and T is obviously measured in seconds. So that is the equation that governs current and charge flow. Now we move on to potential difference. So potential difference is just kind of a fancy name for voltage. In an exam, it will be referred to as potential difference, but it's okay for you to answer with either voltage or potential difference. But just so you know that they are the same thing and they use the same units, which is volts. And potential difference is what comes out of this battery. It's provided by the battery or the cell. We need it to power the components in the circuit. It also provides a current. So you might have seen this equation before, and it's V equals IR, where V is the potential difference, I is the current, and R is a resistance. So in a standard circuit, we tend to have resistance, and resistance might come in the form of a resistor, a thermistor, a light-dependent resistor, or a variable resistor, or a bulb. So you can see that we've got lots and lots of different forms of resistance that can happen in a circuit. So it's really important to remember this equation, V equals IR. You might have also heard it called Ohm's law. Now, the way that this equation works is that if the resistance goes up, so the greater the resistance of the component, the smaller the current will be for a given potential difference. So let's say our battery is 6 volts. Okay, so our battery is 6 volts. It's always going to be 6 volts. But our resistance starts at 3 ohms, which by V equals IR means that the current, if you do voltage divided by resistance, is current. The current is 2 amps. Okay, now if I was to increase this resistance, so instead of 3 ohms, I'm now going to make it 6 ohms, and we do the same calculation, V equals IR. So we have V and we have R, so we divide V by R, which is 6 divided by 6, and now instead of 2 amps, we get 1 amp. So we can clearly see that if we increase the resistance, we decrease the current. Okay, so that's how that equation works. And it's the same as if you were to keep R constant or I constant. If you keep one thing constant, then the other two need to change. Okay, so we talked about Ohm's law, which is V equals IR, the most important equation in electricity, arguably. And that's great for ohmic conductors. So ohmic conductors always follow Ohm's law. Okay, so this is what the current potential difference graph looks like for ohmic conductors. They're kind of like perfect conductors. They follow the perfect law. They work perfectly. They're kind of like the ideal resistor. But that's not always going to be the case, as we'll see later on. So here we have that resistance is constant as current and potential difference change. Okay, so if I make that a little bit clearer to you, we have a graph of current against potential difference. Now, if you know how to find the gradient of a line, you'll know that it's rise over run, or change in y over change in x. We want to find how steep the line is. So you might have heard of tucking a triangle or just doing the change in y over the change in x. However way you want to find the gradient, you can. So to find the gradient of this graph, you have the change in y, which is current, which is I, over voltage. Okay, so that is equal to, if we do I divided by V, that is equal to 1 over R. Okay, not R, 1 over R. If we were going to have R, it would be V over I. Now this is a little bit complicated because sometimes the graph is drawn with current on the y-axis and potential difference on the x-axis, as it is here. Or sometimes they're switched around. So potential difference will be on the y and current will be on the x. So if I draw it the other way, with voltage on the y-axis and current on the x-axis, and we keep the same line, we still want to find the gradient of the line. Okay, so the gradient of the line, is change in y divided by change in x. Okay, so to find the gradient of a line, you have to do the change in y, so how far up it is, divided by how far along it is. Okay, so let's take this point here, and we're going to find the gradient at this point. So how far up is that point? Let's say it's 6.
Hey,
How
Preshayla.
far? Hiya.
Sorry to interrupt. Just quite a few people saying they're not sure or they don't understand this part.
Yeah.
Do you mind maybe just going from the beginning again with this question and just breaking it down a little bit?
Okay, so we'll go back to the beginning. So ohmic conductors follow Ohm's law. Now, Ohm's law is V equals IR, okay? And we can plot this equation on a graph. V equals IR on a graph. Now, you might have heard of Y equals mx plus c, which is the equation of a line. So Y equals mx plus c. So here, we don't actually have a c because you can see that the y-intercept is 0. So we can get rid of the c, which just leaves y equals mx. Now you can see that if we were to plot voltage on the y-axis and I, or current, on the x-axis, which we have here, so voltage on the y-axis and current on the x-axis, our gradient would have to be R, okay? So this tells us the equation of a line. We want to plot this as a line, so we need to match it up. So voltage on the y-axis, current on the x-axis, and resistance as the gradient, which is M. Okay, so that's how we plot a VI graph. Now, we know that the gradient should be resistance. So, to find the gradient from a graph, we have V divided by I, okay, because it's the change in Y, or how far up it is, divided by how far along it is. So the gradient, G, equals V divided by I. The gradient of the graph is the change in Y divided by the change in X, where the change in Y is the voltage and the change in X is the current. So V divided by I is R, resistance. So if we go back over here, this, we can change these out because that might be confusing you a little bit. And we'll make this one I, and we'll make this one V. You can see that the gradient of the graph tells us the resistance. The gradient of the graph is constant the whole way throughout. So it's a straight line, which means it's a constant graph. Okay, so constant gradient constant resistance. Resistance never changes. We can tell that because of the straight line. Okay, so if I take a new graph. Okay, so here, voltage, here, current. And we're going to put some numbers in now so it makes it a little bit more clear. Okay, so we're going to put our line here. Now this is just a graph where V is plotted in the Y, I is plotted on the X. It doesn't mean anything yet. Okay, so now we need to think about how to extract information from this graph, because you will have to do this in an exam question. Okay, so how does voltage change when current changes? And it's all related by resistance. So let's say we have 6 at the top and current is 3. Okay, now to find the gradient of the line, we need to do how far up it is divided by how far along it is. So how far up it is 6, as we can see here, 6, divided by how far along it is, which is 3. So the gradient of our line is 2. Now that's great, but what does the gradient of the line represent? Well, from V equals IR, we can do V divided by I, rearrange the equation to get V divided by I equals R. Now, if you remember, that's exactly what we just did up here. We did V, 6, divided by I, 3. So V divided by I is 6 divided by 3, and V divided by I is also R, so 2 is our resistance. Okay, so the resistance is 2 ohms. So what we've just done is said that the gradient of a VI graph is resistance. Okay, so resistance in this case would be 2 ohms. Now that's really important for you to remember. Voltage, current graphs, and you need to be able to find the gradient and then remember that the gradient represents resistance. Okay, and it all happens because of Ohm's law. Now, following that, Ohm's law is great and it's simple, quite easy to use, but it's not really realistic. It's more of an ideal situation. But what actually happens to resistors in a circuit is that they tend to warm up. And you might have felt it in your phone charger, in your laptop charger, even if you're in school and you're doing the labs, it starts to warm up and up. Okay, so you might feel the battery getting hotter. You might feel components in the circuit getting hotter. That's realistic. If you leave it on for a long time, it's going to heat up. That's what we call a realistic situation. And these realistic situations, unfortunately, don't always completely follow V equals IR, okay? So they are called non-ohmic conductors. Now, non-ohmic conductors just means that they don't follow Ohm's law exactly, okay? So some examples of these are those kind of weird components we saw in our circuit symbols quiz. You might not have heard of them before. They're kind of the weird ones, are the ones that, the odd ones out. So filament lamps, diodes, thermistors, and light-dependent resistors. They are all examples of things that don't quite follow Ohm's law, okay? And before we said that the resistance is linked to current and voltage, but now the resistance is linked to temperature or light. Okay, so now our resistance changes with temperature or light. Okay, so we're going to go through some of the examples really slowly so that you can get an understanding of how these non-ohmic conductors work. So our first example is the filament lamp. Okay, and the filament lamp can be put in a circuit, and we can do calculations with it, and we can investigate it. So a filament lamp, again, we have a current potential difference graph, and we know that the resistance of the lamp increases as the temperature increases. Okay, so what that means is if we have a lamp and it gets hotter and hotter and hotter, the resistance gets more and more and more. Okay, so the resistance of the lamp increases and increases and increases. Okay, if it gets hotter, it's got more resistance. If it's got more resistance, it lets less current through. So this is what our graph would look like for a filament lamp. And you can see that it's quite different to the graph that we had before, which was just a straight line. So now, instead, we have a curved line, okay? And this curved line comes from the fact that resistance changes as the temperature changes, okay? So as we're putting more voltage through, or as we leave it for a longer amount of time, it gets hotter and hotter. If it gets hotter, there's more resistance, okay? And we can see that it doesn't quite follow Ohm's law. If it were to follow Ohm's law, we would have a straight line going all the way through. That would be our perfect resistor, a nice straight line where current is proportional to potential difference. A nice straight line, resistance is constant. A perfect Ohm's law resistor. But we don't, we have a filament lamp, and resistance changes because of temperature. Okay, so it's really important to remember this rule, that the resistance of the lamp increases as the temperature of the bulb or the filament increases. Okay, and when we plot the voltage and current, we get a graph that looks like this. In an exam, you wouldn't have to plot the graph yourself, but you would have to remember what the graph looks like and be able to recreate it in an exam. Okay, so you need to know the component, which is the filament lamp, and the graph that is associated with it, and the rule that governs it. So we have filament lamp, resistance increases as temperature increases, and the graph looks like this. Now we'll move on to the next component, which is called a diode. So you might have heard of a diode before, and it's this circuit symbol here. So the arrow with the line and the circle around it. That's called a diode. Now what's special about a diode is that it lets current flow through the circuit in one direction only. So in a normal circuit, current goes through both ways. Okay, so it can go either clockwise or anti-clockwise, that's fine. But as soon as we put a diode into it, the current flows through in one direction only. So the diode blocks all the current going in the other direction. Okay, so the current can only flow in one direction. The diode has a very, very high resistance in the direction that it's blocking, which makes sense. If it has a very, very high resistance, then there's going to be very, very little current allowed through. Because remember, if resistance is higher, current is lower. Yeah? So if we have a very, very high resistance, very, very high resistance, then there's very, very little current allowed through, which means that all the current can only go through in one direction. Okay, so the graph for a diode, when we plot voltage against current, we have it flowing in one direction, and it looks a little something like this. So a really sharp, steep rising of the curve. And again, you can see that it looks absolutely nothing like Ohm's law, our ideal straight line. Okay, it's absolutely not an ohmic conductor. So you wouldn't apply Ohm's law to a diode. Okay, so we're going to move on to the other two components. So the other two weird ones, which if we go back to our circuit symbols, is this one here. So a thermistor, this one, and a light dependent resistor. Okay. So these are the ones that depend on heat and light. So a thermistor, you might have guessed from therm or thermal, depends on heat, and light dependent resistors obviously depend on light. Okay, so they're two special types of component that can be found in circuits that help us to do certain functions, and they both have rules attached to them, just like the diode did and just like the filament lamp did. So the rules of a thermistor is that the resistance of a thermistor decreases as the temperature increases. Now you have to learn these rules. There's not kind of an easy way, there's not a quick way. These rules just have to be learned, unfortunately. And then the application of thermistors in circuits are when we have things like thermostats in a house. So when the amount of current allowed through, the amount of power supplied to the circuit depends on the heat. So for example, in a thermostat in your home, it might detect, oh, the temperature's too hot. We will cool it down. We'll turn the temperature down in the house. We'll turn the central heating down. Okay, so that's an example of where it's heat detecting and the current depends on that heat. Now, we also have light-dependent resistors. So the resistance of a light-dependent resistor decreases as the light intensity increases. So they're kind of similar in that way. The resistance decreases as the thing that it depends on increases. So here, as heat increases, resistance decreases. As light increases, resistance decreases. Okay, so if resistance decreases and light intensity increases, let's have a think about where that might be used and where that might be relevant in our day-to-day life. So let's say you're on your phone at night and then you suddenly switch off the lights. Your phone may get brighter because you've turned off the lights, and the light dependent resistor helps it to do this. The light dependent resistor detects that there's been a change in light in the room, and so we should make the phone brighter so that the user can see their phone better. Okay, so that's an example of how LDRs are used in real life circuits. So you can see that they're quite useful, and the same for thermistors. Okay, so these are types of resistors that depend on heat and light. Okay, so there's quite a lot of content covered in a short amount of time. So if I go to Frederica and ask if we've got any questions about the content we've just covered, or if you guys want to put on the chat if you've got any questions about what I've just covered before we move on to going through exam questions.
Hey Preshayla, we don't actually have any questions through at the moment.
Okay.
So I guess we have another 15 minutes which you can use to kind of run through exam questions, and then if anyone has any questions, I'll make sure I come to them at the end.
Brill. Okay, so here is our first kind of example exam question, something that could come up in the exam and something that we need to be really sharp on because it's quite common in GCSE Physics. They like to test electricity a lot, mostly because it is one of the hardest topics. So again, don't worry if you don't get it straight away. It is definitely one of the harder topics at GCSE. So this question says that electrical circuits have resistance. Draw a ring around the correct answer. So when the resistance of a circuit increases, the current in the circuit does what? Now this is just a normal circuit that we're talking about, a normal resistor in a normal circuit. So we use our equation, V equals IR. And if the resistance increases, so if resistance goes up, it constricts the current, so current decreases for a constant or given voltage. Okay, so you can see quite a lot of you putting decreases in the chat, which is great. So as you said, if resistance increases, current decreases. Okay, now in the next part of the question, it's kind of like a fill gap exercise. So as I said, it is really important to remember those rules for earlier. An electrical component which has a resistance that increases as the temperature increases is called what? What's that? You've got 3 to pick from there. If the resistance increases as the temperature increases, what happens? Brill, I can see quite a lot of you putting filament bulb, which is great. So as we said before, a filament bulb gets hotter and hotter. The filament in the bulb gets hotter and hotter. And as temperature increases, resistance also increases. So well done if you put filament bulb. Now for the next one, an electrical component which emits light only when a current flows through it in the forward direction is called a what? Now this one's a little bit confusing, but it's actually an LED. So here's a good chance for me to talk about what an LED is. Now an LED is just pretty much a bulb that works if a current flows through it in a certain direction. So we've got a circuit, current's flowing in one direction, and that LED will only turn on if the current flowing through it is in the correct direction. Okay, so that's a light emitting diode. So light emitting is the part where it only emits light if the current flows through it in the correct direction, and the diode part is that correct direction. So it has to be facing the right way to have current flowing through it and it to light up. Okay, so a light emitting diode, an LED, and you might have seen it. It looks just like a little tiny little bulb, but it is very important that you have current flowing through it in the right direction. Only then will it light up. Okay, so that one will be LED. Okay, so the next one. So here we have a diagram which shows a circuit used to obtain the data needed to plot the current potential difference graph for a filament bulb. Okay, so here we're talking about the filament bulb, and if you go back to the rule, if you refresh yourself on the rule, that's temperature increasing, resistance increasing. Okay, so if we zoom in on the circuit, we can see lots of different circuit symbols there. So we have an ammeter here, a bulb here, a voltmeter here, and a variable resistor here. Now remember, a variable resistor is one where we can change the resistance in the circuit. And if we can change the resistance in the circuit, then we can change the current in the circuit. Okay, so we have a variable resistor included in the circuit, which is labelled by J. But why is it included in the circuit? Why do we have this component in the circuit? Why do we need to be able to change the resistance in the circuit? Have a think, 30 seconds, have a think, put your answers in the chat. If you know what it might be, why do you think we might include a variable resistor in the circuit? Okay, so if we have a variable resistor, which is this here, we can vary resistance. Now, by V equals IR, if we can change resistance, then we can change current. Okay, so it would be useful to change the current going through the circuit. Okay, so that is what we use variable resistors for. I'll just write that down. We use variable resistors to be able to change the current in a circuit. Okay, so that's what they're used for. So we use variable resistors to be able to change the current in a circuit. So that's why it's included in our circuit, so that we control and change the current. That's really important, to be able to control and change the current. Okay, so if we can vary resistance, we can vary current. Now, in the next part of the question, we have that the resistance of the bulb increases as the potential difference across the bulb increases. Why does this happen? Have a think. If the resistance of the bulb increases as the potential difference across the bulb increases, why would that happen? Remember, we're talking about a filament bulb here. So what causes that resistance change in a filament bulb? What causes that resistance change? Great, so it's heat, yeah? So heat changes the resistance that we have in the circuit. So again, as heat increases, resistance increases, okay? So that's the main thing that governs it. So and the potential difference comes into it. Well, if potential difference is increased, there's more voltage flowing through the circuit. That means it heats up more. And if it heats up more, then resistance increases. So potential difference causes an increase in temperature, which causes an increase in resistance. Now, I'll write that down for those who want to go back through the lesson when you get a chance. So the potential difference increases, which causes a rise in temperature. This causes the resistance to increase. So it's a chain of things that happen to allow the resistance to increase. Okay, I don't know why it's gotten so big because I pressed small, but never mind. Okay, so next question. So here we have an electrical circuit, and you might notice that this is a question 1, okay? So a multiple choice, 1-mark question, and the question is, what is meant by direct current? So is it current that continuously changes direction, current that travels directly to the component, or current that is always in the same direction? So this one is a bit of a vague one, which is why it's multiple choice. So sometimes when we have multiple choice answers, they tend to give us three options, which are quite similar. So for this one, it is really important that you know the exact definition of direct current. Okay, so direct current is current that is always in the same direction. Okay, so always in the same direction. Current that continuously changes direction is a different type of current, and it's called AC current. And you don't need to worry about it. We don't need to cover it. It's not in your exam board, but that would not be the correct answer because it's a change in current. So you might have heard of AC and DC. Here we're talking about DC, which is direct current. AC is alternating current. And that would be the first box, current that continuously changes direction. And then current that travels directly to the component, that's not a certain definition. It's just that current does travel to the components, but sometimes it needs to go through a component first to get to the next component. So our answer here would be current that is always in the same direction. So that's direct current. And you'll be dealing with direct current for the majority of all the topics in electricity for your GCSE. So you don't need to worry about the current changing directions. It's always in the same direction. Okay, so I think we have time for one last question, which is the equation links current, potential difference, and resistance is potential difference equals current times resistance. I think I've said that a million times. It's V equals IR, okay? So they want you to calculate the potential difference across the battery in the circuit. So if we go back to the circuit, we want to find voltage. So we have our equation, V equals IR. We want voltage, so we need to do current times resistance, where our current is 0.4 and our resistance is what? Now this one's a little bit more complicated because we have two different resistors. Now if we have two different resistors, we need to add the resistors together. So if we add 20 plus 10, we get 30. So that is now our total resistance, 30 ohms, and then we can put it over here into resistance in our equation to get that the voltage equals 12 volts, which some of you are putting in the chat, which is really great. So potential difference or voltage in this circuit is 12 volts, which we get from doing current times the total resistance in the circuit, which is 30 because we added them together. Okay, so I think we'll stop there with the exam questions for now. If anybody does have any questions, if we don't, then we can carry on.
So we do have one question, which is just, can we do a harder one?
A harder one. Okay, cool. We can definitely do a harder one.
And then if there aren't any more questions, we can just carry on with other ones until till the end.
Great. Okay. So here's a slightly different one, which includes a new equation that we haven't covered yet. So this equation is P equals IV. Okay, P equals IV, where power is current times potential difference. So it's not to be confused with V equals IR. They're two completely different equations. So P equals IV is current times potential difference, and we're going to apply it to this circuit here. So what is the power coming from the battery? Power equals current times voltage. Our current is 0.4 amps, and our voltage, which we just worked out, is 12 volts. So if we want power, we need to do power equals IV, and I equals 0.4, and V equals 12. So 0.4 times 12 is 4.8. So if you've got 4.8, that's great. But what is power measured in? What unit is power? What units do we use for power? So power is amps times volts. And do we know what that equals? Cool. So Michael, you got it correct. It's watts. So 4.8 watts. Well done if you said watts. Joules is for energy. So we use joules for energy, and coulombs for charge, and watts for power. Okay, so watts for power. Okay, so that was a slightly different one, not necessarily harder, but we can get a harder question. Okay, so this one's quite a bit harder. So here we've got a kind of experimental question. So it's you kind of using your own kind of ideas about how circuits work and setting up a circuit to investigate a certain thing. So here we have how the current through a filament lamp affects its resistance. So how could we set up a circuit using these 5 components to help us to investigate the current through a filament lamp? So have a think. I'll just give you 30 seconds to think about how that circuit might be set up. So we need to be able to investigate how the current affects its resistance, which means we need to talk about how resistance changes, which means we need to take measurements of resistance. Now, we can't take measurements of resistance, but we can take measurements of voltage and current. And obviously, when we divide them, we get V equals IR. V divided by I is R. So we need to take voltage readings and current readings of our filament lamp to be able to find the resistance of the filament lamp. So our circuit would look a little something like this. So we've got our battery here. And we're going to connect it up. But what are we going to connect it up to? Well, we need to have our filament lamp in the circuit. That's a must. That's the thing that we're measuring. That goes there. Now, our variable resistor also needs to go in the circuit. But before we put the variable resistor in, we need something else that goes in series with the component that we're measuring. What out of these 5 symbols always goes in series with the component that we measure? It's great. So I can see some of you saying an ammeter, which is perfect. An ammeter always goes in series with the bulb. Okay, so an ammeter goes in series with the bulb. Then we can put our variable resistor in. And we can join our circuit up to make sure it's a closed circuit. But we're missing one circuit symbol, which is the voltmeter. Where would the voltmeter go? Great, so I can see some of you saying that the voltmeter is around the filament lamp or the filament bulb or in parallel with it, which is great. It is absolutely in parallel with it. We never put voltmeters in series with the component that we're trying to measure. It always goes in parallel. So our voltmeter would go there. And that is how we might be able to set up a circuit to help us investigate this statement here. Now, how would that experiment work? So this is probably one of the more complicated questions that you'll get in the electricity topic, and it's describing experiments. When we describe experiments, we have to make it absolutely crystal clear in a logical set of instructions what happens and why it happens and what the next step is as a result of that. So the first step would be to say that the battery provides a voltage to the circuit. Okay, so that's might seem obvious, but we need to include it. So we switch on the circuit, we connect it to the battery, we have a potential difference flowing through. The ammeter is used to measure current, and the voltmeter is used to measure voltage. That would also get you a mark. So not too complicated yet. And then we need to use the fact that we talked about earlier. So because we have this variable resistor, we can change resistance. Variable resistor, so we can change resistance. Okay. Now, if we can change resistance, then we can also change current. Okay, so this variable resistor would be used to change current in the circuit. Okay, and if we change current in the circuit, we can get lots of different readings for current. So changing current allows us to take lots of different readings. If we change the current through the filament lamp, we can also take readings of the voltage. Okay, so we can take readings off of the ammeter and off of the voltmeter at each different change of the variable resistor. So let's say we set the variable resistor to 2 to start with. We took a reading of ammeter and we took a reading of the voltmeter. Then we change it to 3, take readings, change it to 4, take readings, and so on and so forth. Then we might have a list of 10 different readings of voltage and current. Now, because we have readings of voltage and current, like we always do in an experiment, we plot a graph. Okay, and what you should see, and you won't have to do this in the exam, but what you should see is that graph we saw earlier, which looks kind of like a snake, right? So we saw that voltage current graph earlier. So that is the filament lamp voltage current graph. Okay, so the last point in your answer would be plot a graph of all the different voltage readings and all the different current readings. And then we can find out the resistance by doing V divided by I for the linear part of the graph. So we can change the current because we can change the resistance. If we change the current, we get different readings of voltage for constant resistance. So that would be how that experiment works.
Cool. We just had a question about that. Two people asked why the resistor would change anything to do with the filament lamp.
Okay, so changing the variable resistor changes the current that goes through the filament lamp. So we're going to have a different current that goes through the filament lamp. And if current changes through the filament lamp, then that affects its resistance. So because if we have a current, if we have more current, we get a hotter lamp, which means we have an increased resistance. So as current increases, temperature increases and resistance increases.
And then we had another question, which was, would you need to label the circuit with this type of question?
So you wouldn't need to label the circuit, and they've given you the circuit symbols, so that's fine. You just need to draw them in. So you don't need to label that that's the variable resistor. You just need to put it in the circuit.
And then another question in asking if the voltage changes when the variable resistor changes.
So if we change the variable resistor, the voltage does in fact change from the filament lamp. So the current through the filament lamp changes, which means that the voltage of the filament lamp also changes because of V equals IR.
Cool. Thanks, everyone. Just 1 minute or 2 minutes left now. So there's quite a few questions that I've had come through for me, which are there any more lessons this week and for which subjects? And also, when are the next lessons? So just a general question around lessons, basically. So there are going to be physics lessons and maths lessons for the rest of this week, every day for the rest of this week. The maths lessons are running at 12:15. And if you were in one of them earlier today, then you would have heard me say this, but the physics sessions will be running at 2 o'clock every day for the rest of the week as well. So look out for links on the My Tutor online school landing page to all of the sessions, and you should be able to sign up that way as well. Just had a question come through asking if we're going to have biology or chemistry sessions. Yes, for this week we will have a lesson on biology and a lesson for chemistry, so also look out for that too. And I think that's everything. So just a final thing to say that thank you so much for joining us again, and this lesson has been recorded, so you will be able to find a link so you can watch it back, and yeah, look out for the other lessons that will be coming up the rest of this week. Thanks everyone, have a good day and see you soon. Bye.